Hello, my name is Wesley Costa. Now I'm the corresponding author and the presenter of this research entitled Performance Evaluation of a Soft Handover Framework Applied to VLC Systems. This work was produced by the Visible Light Communication researchers of the Telecommunications Laboratory, Labitel, located in the Federal University of Espírito Santo. So, here I present a quick overview of what we're going to talk about. This presentation is divided as following. At first, I introduce the motivation of this research, the implementation of VLC, the problems, and some approaches used in the literature, like the handover. Then the methods here are presented. After that, the application of the methods presented culminates in some results to be discussed. To finish, the conclusion of this work are shown. As addressed by Cisco Annual Internet Report in 2023, it is expected that about 70% of the global population will have mobile connectivity. The problem with that is that this growing may find some challenges in the limited radio frequency spectrum, so new technologies are welcome. Visible light communication, also known as VLC, is a great alternative for the increase in data demands. However, one VLC access point provides a low coverage of about 2 to 4 meters in diameter, which can be increased by using many access points. Thus, mobile users will need their connections to be switched between access points. To overcome this drawback, we have two approaches. One is hard handover. It occurs when the users need to first finish the connection with the current IP and then start a connection with another. And the second one is the soft handover, when the users start the connection with the next IP before disconnecting from the current one. In this paper, we evaluate the performance of a soft handover scheme in a line of sight VLC system that comprises two access points and one user. For the simulation environment, we implemented a control unit to manage the access points, which can be seen as distributed antennas. We also used the two access points and one user, implementing a downstream multiple input and a single output, called a meso system. Each access point was placed 1.5 meters above the user's photodiode, and each one covered 3.57 meters in diameter, as can be seen in this figure 1. The signal transmitted was an orthogonal frequency division multiplexing, as parameterized in this table. The bandwidth of 1 MHz, the FFT size of 16 points, 5 data carriers, and 4 km mapping. Then the signal was replicated in two different bands, one centered in 3 MHz and the other centered in 6 MHz. This approach allows the user to receive the same information in two different bands and choose the best signal to recover the data. Thus, the user can make a soft handover between the access points by analyzing their received signal strength indicators, also known as RSSIs, as shown in the equation here. The simulated tests were done by implementing a DCO OFDM, which stands for Direct Current OFDM, where Hermitian symmetry was applied to provide real OFDM signals. The LED was simulated considering only its linear region, shown in the blue shaded area of the figure. And its equation is described by PLD equation, where Pmax is the maximum output power, zeta is the adjustment constant, K is an effector, and ILD is the modulated amplified current plus the DC bias. We only consider a line of sight channels because the paper's focus is on the handover process. Thus, the received optical power, PR, can be calculated using the channel DC gain H of 0, which is defined as shown in this equation. This channel parameters used here is described in this table 1. The handover strategy used here was the following. The user receives two signals from two access points centered in different frequencies at the same time. This can be seen in figure 3. The user chooses the signal with the highest power that is calculated by the received signal strength indicator, RSSI, in dBm, from each FDM signal. In this case, RSSI of the AP01 and the RSSI of the AP02 received the signals were almost the same, so the user is in the section region. The figure 4 shows the base distribution along the route, and the route is described as this dot dashed green line in this figure. So there is a signal coverage along the entire route, allowing the user to keep connection by receiving signal from AP01 from the beginning until the middle of the intersection. When the RSSI from AP02 starts to be greater than the AP01, the users consider the signals from AP02 until the end of the route. We also used EVM for the evaluation of the system proposed. The figure 5 depicts the EVM along the same route explained before. Due to the line of sight, the EVM drops instantly when the user reaches the field of view. The figure 5 also shows better EVM for the AP02 than for AP01. It occurs because the intermodulation distortion is more intense in lower frequencies. As described earlier, we consider two access points. In this case, we have the user inside the region of the access point 01. So the RSSI of the signal coming from the AP01 is greater than the RSSI of the signal coming from the AP02. So we choose the signal coming from the AP01. In this case, we have the user inside the intersection region. So we have to acquire the signal that has the greater RSSI. In this case, we have the user inside the region of the AP02. So the constellation is better than the AP01 signal. And then we have to acquire the signal from the AP02. To finish, the conclusion and future works. This paper presented a visible light communication soft handover scheme using received signal strength indicator as a metric to choose the best signal. Simulation results show satisfactory error vector magnitude in all user trajectories, allowing the maintenance of suitable connection, including the handover. The results demonstrate that this approach is an alternative to increase VLC network coverage without connection loss. For future works, the dynamic resource allocation can be applied in cell-free networks and the application of non-orthogonal multiple access to improve spectral efficiency. We'd like to acknowledge the Brazilian funds government agencies called FAPES, CNPq, CAPES, and the project that we've enrolled called Núcleo de Estudos em Tecnologias Emergentes para 5G, the NEST 5G, Aplicação de Tecnologia de Comunicação por Luz Visível em Monitorização de Recém-Nascidos de Alto Risco, and the Brazilian and Germany project called Optical Wireless Systems with Imoc Architecture in an Industrial Environment, called WIND. That's all. Thank you for watching this presentation.